Hi everyone, welcome back. We are on day 2 of related rates. So in these problems, we are going to be looking at problems that use trigonometry and problems that use some geometry formulas. All right. So ship A is traveling due west toward Lighthouse Rock at a speed of 15 kilometers per hour. So that means ship A is heading this direction. And then ship B is traveling due north away from Lighthouse Rock, so that's going this direction at a speed of 10 kilometers per hour. Let x be the distance between ship A and Lighthouse Rock at time t, as shown in the figure. We've also got the distance between Lighthouse Rock and ship B is y. And then I'm going to go ahead and I'm going to put a z and call that the distance between ship A and ship B. So let's take a look at what's going on here. Question A, or part A, says find the distance in kilometers between ship A and ship B when x equals 4 kilometers and y equals 3 kilometers. So hopefully you guys can look at this and you can see right away that this isn't even a related rates problem for part A. So for part A, we're just looking at, okay, here's ship A, here's ship B, here's the lighthouse. We know that x is 4 kilometers and y is 3 kilometers, and we're looking for z. So this is just a nice straightforward Pythagorean theorem. So if we go back to our original, it's x squared plus y squared equals z squared. So we can just go ahead right away and say that 4 squared plus 3 squared is equal to z squared. And if you know your Pythagorean triples, please just go ahead and do it. We get that z equals 5 kilometers, right? It's a 3, 4, 5 triangle. 16 plus 9 is 25, and we take the square root. So that's easy enough. Hopefully you guys can look at it. Hopefully you know your 3, 4, 5 at least. Hopefully. Okay, so part B says find the rate of change in kilometers per hour of the distance between the two ships when x is 4 and y is 3. This is definitely a related rate because now we're talking about a rate of change. So let's go ahead and draw our picture again. Here's ship A heading this direction. Here's ship B heading that direction. There's our lighthouse in the middle there. And we know this is x, y, and z. So this is actually very similar to the ones we were doing in class today. So we can actually just go right ahead and use Pythagorean theorem to write an equation. So x squared plus y squared equals z squared. This is no different than what we did before. Now remember, we didn't plug in any values here for x, y, or z because all three of these values are changing all the time. So remember, when we write our equation, the only numbers that we would use in our figure are numbers that are constant, and none of these are constant. So we just use the variables. So now we can go ahead and take the derivative, and remember, we're going to use implicit. So 2x dx dt plus 2y dy dt equals 2z dz dt. And now we're going to write out our variables. Oops. So we've got x and dx dt, y and dy dt, and then z and dz dt. All 6 of those are actually unknowns in this equation right here. So we know that x is 4 kilometers, y is 3 kilometers, and if we pay attention, part A, that's the same x and y that we had, and we already found z to be 5. So we don't even have to do the work again, but if we had to, we would just do what we did in part A. But let's read the problem again and see what else we know. So ship A is traveling due west toward the Lighthouse Rock at a speed of 15 kilometers per hour. So since this distance is getting smaller, we know that this dx dt is actually negative 15 kilometers per hour because the distance is decreasing, so it's got to be a negative rate. And then ship B is traveling away from the lighthouse, so that's a positive 10 kilometers per hour. And if we look, the question is asking for the distance between the two ships. That's our dz, the rate of change for the distance. That's our dz dt that we're looking for. So now we're just going to plug in what we know and solve. So we have 2 times 4 times negative 15 plus 2 times 3 times 10 equals 2 times 5 times dz dt. So 2 times 4 times negative 15, we get negative 120, plus 2 times 3 is 10 is 60, equals 10 dz dt. Negative 60 is equal to 10 dz dt, and if we divide by 10, we get that dz dt is equal to negative 6, and we need some units here, kilometers per hour. So when we think about it then, it's saying that the distance between the two ships is decreasing because it's a negative 6. So it's decreasing at 6 kilometers per hour. Okay, now part C is where we get into something that's a little new. So part C says let theta be the angle shown in the figure. Find the rate of change of theta in radians per hour when x is 4 kilometers and y is 3 kilometers. So we are going to need to redraw our picture here. This one's going to be a little bit more work, but here's the theta that we're talking about. And we know this is x, this is y, and this is z. And now we need an equation that relates theta, x, and y, because those are the variables that we have. So this is where our trig comes into play. So if this is theta, then we know that y, which is across from it, is the opposite side. And then x, which is right next to it, is our adjacent side. So I'm actually just going to opposite and adjacent. So those of you who had me for geo, hopefully you remember this. But that means then that the tangent of theta is equal to the opposite, which is y, over the adjacent, which is x. Because if we think about trig, we know that we need our SOHCAHTOA. So there's our equation that relates theta, x, and y. So we have our picture, we have our equation, now we're going to take the derivative. So the derivative of tangent of theta is secant squared theta, d theta dt, because we need to remember we're doing implicit differentiation here, equals, now we do need to be careful here because y over x, this means that we're going to have to use some quotient rule. So low d high minus high d low, so low d high is going to be dy dt, minus high, which is y, d low, dx dt, all over low squared. So that is actually what we get when we take our first derivative, okay? Now we're going to go over to the side and we're going to write out what we need. So we need an x and y, and we also need theta, and then we're going to need dx dt, dy dt, and d theta dt. So let's think about what we know. Well, we know that x is 4 and y is 3. And we already know the dx dt and dy dt. So that's just our negative 15 and positive 10. And it's asking us to find the rate of change of theta, which means d theta dt is what we're going to be solving for overall. Which means we're still trying to find theta in order to be able to use this problem. But here's where things are going to get a little different. We're not actually going to solve for theta because that would require a calculator. So instead, we're going to solve for the secant of theta. And we're going to do that using our right triangle. So we know at this specific point in time that x is 4, y is 3, and we've already used Pythagorean theorem or a triple to solve for the hypotenuse, which is 5. Now we know that the side across from theta is the opposite. This is our adjacent, and this is our hypotenuse. And we want to find the secant of theta. we know that secant of theta is equal to 1 over the cosine of theta. And we know cosine is adjacent over hypotenuse, which means that secant is the hypotenuse over the adjacent. So hypotenuse is 5 and adjacent is 4. That means we found that the secant of theta is 5 over 4. So like I said, this allows us to do this problem without a calculator. We don't have to actually solve for theta because we can find the secant of theta just using our triangle. So now we have all the information. Now we're going to need to plug it all in. So I'm going to kind of box this off. All right, so secant squared theta, so that means 5 over 4 squared d theta dt is going to equal x, which is 4, times dy dt, which is 10, minus 3 times negative 15, all over x squared, so all over 4 squared. Okay, and then we need to solve that. So 25 over 16 d theta dt. Let's see, we've got 40 plus 45, so that's 85 over 16. So d theta dt is going to equal 85 over 16 times, I can multiply by the reciprocal, so 16 over 25. And we can cancel those 16s. We can take a 5 out, so we actually get that it's 17 over 5. I do want to write my final answer in kind of a nice box over here instead for you guys though. So d theta dt, which was what we were looking for, is 17 over 5, and we know that the units are radians per hour. And so there's our final answer there. So we had this little bit of a trick of finding secant of theta instead of actually finding theta. But other than that, it shouldn't be too bad, hopefully. I don't know. I guess we'll see when I see you guys tomorrow in class, or on Monday in class. Okay, the second type that we are going to talk about is area and volume formula. So we're going to use some formulas from geometry. So when you guys come back into class on Monday, we're going to go back to the other page where we wrote down some of our formulas and just kind of fill those in. I'm not going to waste time in the video doing it. All right, these should actually be pretty straightforward as long as you know your formulas. So memorize, all right, people? A crowd gathers around a movie star forming a circle. The radius of the crowd is increasing at a rate of 3 feet per second. All right, so we've got a circle. It's a nice picture. And here's our radius. Okay. How fast is the area taken up by the crowd increasing when the radius is 15 feet? So that means we've got a circle and we want to talk about area. So area of a circle is pi r squared. There's our picture. There's our formula. Time to take the derivative. So dA dt is equal to 2 pi r dr dt. So for this problem, we need to talk about r, we need to talk about dr dt, and we need to talk about dA dt. So now's the time where we go back to our original problem and figure out what we know. So the radius is increasing at a rate of 3 feet per second. So that's my dr dt. How fast is the area taken up by the crowd increasing? So what's dA dt? When the radius r is 15. And now we just plug in. So dA dt is going to equal 2 pi times 15 times 3. So dA dt is equal to 90 pi, and now I need some units, feet squared per second. I know it's feet squared because it's dA. I'm talking about the area. So the area is increasing at a rate of 90 pi feet squared per second. That's it. That should be nice and straightforward. All right, then we've got this cube growing at a rate of 64 cubic meters per minute. How fast are the sides of the cube increasing when the sides are 3 meters each? So we're going to draw a cube. And we know that every side is x. And we're looking at, let's see, 64 meters cubed. That means we're talking about volume. So the volume in this case is just x cubed. So we're going to go ahead and take the derivative, dv dt, 3x squared dx dt. So we need x, we need dx dt, and then dv dt. So let's see what we know. For this one, we're saying that the cube grows at a rate of 64 cubic meters per minute. Well, in this one, you'll notice they gave us the rate of the volume changing. So that's where our 64 goes. How fast are the sides of the cube, so dx dt, increasing when the sides are 3 meters each? So x is 3 and dx dt is what we're looking for. So in this case, 64 equals 3 times 3 squared times dx dt. So 64 equals 27 dx dt, and then we can just divide that over. So we get 64 over 27 meters per minute. And there we go. All right, one more quick problem. So a spherical balloon is inflated so that the radius increases at a rate of 4 centimeters. Okay, if the radius is increasing, this should just be centimeters, not centimeters cubed. Centimeters per second. How fast is the volume of the balloon increasing when the radius is 5 centimeters? So let's draw a balloon. There's my balloon. And I'm going to make it look like a sphere right here by just doing that. All right, and then here's my radius r. I know that the volume of a sphere is 4/3 pi r cubed. I'm going to take the derivative using implicit, so dv dt is equal to 4 pi r squared dr dt. And now I'm going to think about what I need. So dv dt is something, and r is something, and dr dt. Okay, so radius increases at a rate of 4 centimeters per second, so dr dt is 4. How fast is the volume increasing, so what's dv dt, when the radius is 5? All right, so let's just plug in what we know. So dv dt is equal to 4 pi times 5 squared times 4. So we get that the volume is changing at a rate of, let's see, 16 times 25. So we get 400 pi. And now I need centimeters cubed per second, because now I'm looking at the volume changing. Okay, that's it then for this. So maybe do yourself a favor and box the formulas and put some stars by them. So that's a formula you need to know: volume of a sphere, volume of a cube, area of a circle. And then I guess the other thing that I would write down would maybe be SOHCAHTOA. Because we did use that for the trig one on the front. So if you are going to flip back and fill in your formulas already, you can go ahead and do that. Those would be the 4 things I would write down. Otherwise, we're going to do it in class when I see you guys on Monday. I hope this all makes sense. Ask questions on Monday if it didn't. All right, have a great weekend.